laser. Então, ok. Show. Pode. Obrigado.
Okay, our next speaker is Thiago Gerreiro from PUC Rio. He's going to talk about tabletop fundamental physics experiments. Thank you.
Thank you very much. So first of all, thanks the organizers to invite me here, and also the entire quantum information community of Brazil, which has been very welcoming since I came back in 2017. So I want to tell you about some recent developments and the beginning of a new lab at PUC Rio. It's a university in Rio de Janeiro. Many people, especially outside Brazil, don't know this place, so I want to start introducing the university. And also some people in Brazil have some ideas about the place which are not quite correct. I know. So this is a Google image of the campus. So you see there are some buildings here, but it's mostly trees. It's inside a park. Perhaps the most important and relevant information is the distance we are located from the beach. So if you ever come there, it's a nice opportunity to go for a swim. You know, it's a nice campus, a lot of people. We have all sorts of creatures around the campus, so it's a very nice environment, you know. So it's a, very good PhD students and master students. So anyway, for the people of Brazil, I don't know what you've heard about PUC, but you do not pay to do a master or a PhD. It's like any other university, you know, you apply for a CNPq scholarship and you get it, and you can do your master and your PhD, so please come and do a PhD here. Anyway, so I was working in Switzerland, in Geneva, in the group of Nicolas Gizan for many years. I did my PhD there, and eventually there was a opening at this university and applied, and I got the position. So I'm an experimentalist. I wanted to build a lab, you know, but it was quite free, you know, when you have to come up with ideas and figure out what you want to do out of your life. So I've established a mission for myself. I really like fundamental physics, and I would like to use the knowledge that I acquired in quantum optics and the things that I learned into doing fundamental physics experiments. So the sort of mission that I performed for my life, let's say, is to perform one day. I'm not saying I'm going to do it next year or, you know, in 10 years. Maybe I'm probably even not going to do it because it's such a hard thing, but it's worth trying and it's going to be fun. So the idea is to perform a physics experiment for which we have no clue what the answer will be. Okay, that's what would be the dream. Let's say it's a goal I set for myself. But that's very romantic, very nice. But what can you do? Like, you know, what don't we know about physics? You know, what don't we know about nature? Where could the new physics be waiting to be discovered? So if you think a bit and you study and you read and you meditate on it for a while, you figure out we don't know many things, actually. Actually, we don't know almost anything about the universe, you know? It's an illusion. People say, it's like Lord Kelvin said physics is over in the 19th century. I think we're at the same border now. So it's within the next 100 years or so, maybe we'll figure out new things. So first of all, we don't know how galaxies are kept together. We don't know what 70% of the universe is made of. Probably that's new particles. We don't even know that for sure, but that's the best guess, you know, if you want to be conservative. And we know within quantum field theory, for example, that new particles can imply new forces. Okay? We also don't know like what's happening out there. I mean, recently we discovered gravitational waves, which is a new window into the universe, and that will open great avenues. You know, it's like a new branch of astronomy that was born. We have this fantastic instrument. It will allow you to see deep into the universe and in channels which we've never seen before. So there could be surprises there. And I'd like to point out, you know, that this is an interferometer. It's a quantum optics experiment. It's low energy physics. You know, you don't need to have a huge collider, such a immense trillion-dollar experiment to discover a new thing. I mean, okay, this is several $100 million, but anyway, it's still cheaper. So all this I did within the first year I was at PUC. I was in the process of figuring out, you know, what kind of setup I'm going to build. I'm an experimentalist. I know quantum optics. I have to figure out some, you know, new direction. What's the setup? Am I going to do just laser physics or just quantum optics, or am I going to do atoms? I don't know. So I was, you know, thinking about this for a while. I mean, we also don't know why the universe is so big. This is, I phrase it in this way because I think it's the nicest way of putting it. Actually, it's a cosmological constant problem. I mean, the universe is expanding at an accelerated rate because there is a sort of vacuum energy, and the density of this vacuum energy is so small. Actually, it's inversely proportional to the radius of the observable universe. We don't know why that is. And the best candidate is really vacuum energy, but if you estimate naively what the contribution that should be, it's way, way, way much bigger than what we measure by looking at galaxies that are receding. And okay, you can probe the quantum vacuum with sort of optomechanics experiments. No? You can have like a cantilever here, and you can measure Casimir force. You can do torsion balances. Then you can use this to compare it with astrophysical constraints. So it's also something we don't know about the universe. And more familiar, perhaps, to most of us here, is that we can still test quantum mechanics in different scales, you know, and try to see if it applies. So that's a good way to go. So fundamental test of quantum mechanics, I mean, you never know. Maybe one day you will put a 1 kilogram mass in a superposition of two different places, and you will figure out that it behaves in a different way from the quantum prediction. I don't know. Who the hell knows? So after meditating for a year, you know, I read a lot about other experiments. Actually, there is a small silent community of low-energy physicists like us, like quantum opticians and atomic physicists who are looking for new physics. And there's a whole bunch of experiments. We don't hear much about them because they haven't discovered anything yet, but that's okay. I mean, not discovering something is also a discovery, you know. You can always, if you figure out that something that you expected actually don't exist, it's relevant information. That's real physics, in my opinion. Here are some examples. You can have experiments that try to measure the vacuum birefringence. So the idea here is you apply a huge magnetic field in vacuum that will polarize electron-positron pairs. You send a laser light, and you expect the polarization to rotate. I mean, this is a real effect. It exists. QED predicts it. It has never been measured, but it's there. And it's nice. It's also a quantum optics experiment. It's a polarimeter, you know. You just have to be very, very sensitive to polarization rotation, and then you will see this quantum vacuum in action. You can do searches for dark matter on nuclear magnetic resonance. For example, there are some predictions that if you have this scalar axion, pseudoscalar particles, they induce a permanent dipole moment in nuclei, and you can look for it on nuclear magnetic resonance. Torsion balances, and more recently you can have optomechanical systems like levitated microspheres, and you approach some bulky matter to that, and you try to look for gravity or even other forces which you didn't know existed. So there are all these examples here and many more. So after all this, you can look at the idea, of course, is to use very precise experiments to search for new physics. So there are not many possibilities if you want to attach to our current understanding of physics and you don't want to go too much crazy and invent your own theory. There are a few possibilities on what new physics could be out there. You can add particles to your theory. You can add scalar or pseudoscalar or vector or axial vector particles. These are also relevant for people who do dark matter models and things like this. So, and you can also predict what new effect, what new measurable physical effect these modifications would get. So for instance, if I add a scalar particle like this, it couples to some standard model quantity. It could be anything. I will show an example of this later. This would lead either to a variable mass, so like particles would have slight variation in their mass as they go along, or accelerations or new forces. Also for vectors, you could have acceleration and so on. And you can add higher spin particles and you have other effects. But okay, there's no reason in contemplating higher spin if you don't eliminate these possibilities here first. So what did I decide to do at the end after 1 year of thinking? I decided, okay, the mission is to set up a quantum optomechanics lab. I think that's the most promising avenue for going for new physics, at least for me, like combining with what I know with all the quantum optics and things, and then perform a physics experiment for which you have no clue what the answer will be. Now, of course, this is still it's a very ambitious task. Not saying I'm going to do it in the next 2 or 3 years, but it's the goal I want to pursue. So with optomechanics, you can probe this kind of acceleration effects here. That's the idea of what we're going to do. So basically, you can look at the force and displacement sensors that you can build with optomechanical system. Here are 2 examples. So you can have this sort of a micromembrane, nanomembrane in the middle of a cavity, and as a light which is resonant with the cavity propagates through. If the membrane moves, it changes the resonance frequency of the cavity, because the dispersive element inside the cavity, something moving there. And by monitoring the back reflection from the cavity, you can actually know how much the membrane moved. And people have demonstrated this. I mean, this is a standard tool in optomechanics labs. Several quantum optomechanics people around the world have this. So this is one possibility of a force and displacement sensor you could use. You can cool it down with passive cooling. You know, you send a detuned laser into the cavity, and the dynamics cools down the center of mass mode of this membrane, and so on. And you could have microspheres. So you levitate these things with radiation pressure. You have different regimes. You could use gradient forces if the sphere is very small, or if the sphere is bigger, you just rely on radiation pressure to levitate it. And you can also use it as a force and displacement sensor. And you can also cool it down. I mean, this is our power spectrum I took from these people at Stanford. They're doing some experiments along these directions. So the idea, why not combine both? You know, so we have two nice force and displacement sensors, and so we can invest in two different technologies and eventually even combine them and put them together into a single experiment. So the experiment I'm trying to build now, so it's very, very at an early stage. I mean, it's been a few months. We've been actively in the lab building this thing. I'm going to show you pictures in a second. So the idea is to levitate a microsphere inside an optical cavity and near this membrane. And then approach them very, very close and look to see if one of them moves. Okay, so this, simple as that. So maybe new physics will come in a stupid thing like this, you know. Of course, it's very hard, very technical. I mean, there are several problems. There are several backgrounds. Like, there are other forces that you don't want in your setup, that they could be present there, then they will probably be present there, and you have to characterize them and eliminate them very well. And that's what makes it hard. That's the very difficult part. But that's the general idea. So you can probe axion-like particles, scalar particles with this. Eventually, in the future, you could like develop such a sensitive sensor that you could be able to place constraints into new particles and new forces of nature associated to those particles. So I also spent some time thinking about what the name of the experiment would be. That's very important. If you want people to believe in you, you should have a nice name. So I came up with this scalar axion-like microsphere brain apparatus, which stands for SAMBA, which is a very Brazilian thing. So yeah, you guys will remember, if SAMBA ever flies off and we measure something nice, then we're going to have SAMBA. So okay, I say here the membrane is quantum. Essentially, the resonance frequency typical of these things is around hundreds of kilohertz. And I mean, anything which has a resonance frequency which is high enough, you can say this closer to the ground state, right? It's easier to cool it down, say at room temperature. Whereas the microsphere is classical, it's very far away. This has a resonance frequency around, say, 100 hertz, so it's very far away from the ground state. I mean, it's thermally dominated. It's dominated by thermal motion, even if it's in vacuum. So, but this is not really important. So the idea is to, you know, start building these things and place them together and see, you know, develop the technology and go towards measuring looking for these forces. Okay, so that's the general program. This is a more detailed setup. I mean, don't trust this picture too much. It changes every week, and yeah, sure. Yeah, sure. That's an excellent question, and the honest answer is I don't know. So the thing is, I wanted to invest in I wanted to start two different things at the same time. You know, of course, I mean, you buy these membranes from a company in Canada or whatever, and you buy them on a pack of 5. So you could place more membranes. You could test, and that's in our pipeline. We're going to try to do that. But it's nice also to invest in a different thing. You know, if it turns out that the microsphere, for some reason which I don't yet know, it's much better than the membrane, we also developed that in the process. You know, there's a branch that goes along that direction. But there's like an infinity of things to test. So yeah, this setup, it changes every week. I mean, basically, we discover we have something in the lab that I didn't know we have before, so that simplifies stuff. Or sometimes we discover we don't have stuff, so this picture changes every time. You know, the only thing which is really fixed is the wavelength of this laser, which monitors the membrane. Because I decided to buy this Toptica laser at this wavelength, partially because I can also do other quantum optics experiments with it. So this is a nice wavelength. If you down convert it, you're in the telecom regime. I have some experience with telecom light, so it's a nice, I thought it was a nice way to invest. And that basically fixes the width of the membrane, because you want to maximize the reflection of the membrane with respect to I mean, you want the wavelength that you send in to have as much reflection as possible, so it interacts mostly with the membrane. No? In the limit that the membrane has 0 reflectivity, as if it's not there. In the limit that it has 100% reflectivity, it's like a moving end of the cavity. So you want to maximize this. Well, it's not even, yeah, in principle you want to maximize, but it's not so clear that that's the optimal as well. But anyway, this wavelength here that levitates the microsphere is also important, because you want to minimize the scattering of light. Well, there will be scattering of light in the microsphere, and these photons will hit the membrane and they will make it move, and that will give you an effect. That in principle it's a background noise for whatever force you want to measure. So you want to choose a wavelength which the membrane couples very little to. So there's this reflectivity curve of the membrane, and it has a dip for 100 nanometer thickness membrane. It has a dip around 470 nanometers. So it's the least you could interact with it. So that's also a choice of wavelength that you want to levitate. So anyway, these are some back of the envelope general expected characteristics of the setup. And as I told you, this is not built yet. We are in the process of building it, so these are all very rough estimates. But just to give you an idea, you know, this membrane is millimeter size. The microspheres, they are micrometer size. They could also be some 100 nanometers, so like 0.1 micron. The masses are around 10⁻⁴, 10⁻13 kilograms, so it's very light objects if you think about everyday life. But if you think in terms of atoms, it's very heavy. There are several atoms stacked together, no, to make this membrane and this microsphere. The resonance frequencies are very different. This is also a nice thing about investing in 2 separate systems at the same time, so you can play with 2 different devices. And one thing that I want to point out is that these kind of systems, they have a sort of sensitivity to displacement and force and acceleration, which are incredibly nice. So you see with this membrane here, and these are numbers which, I mean, you calculate them as estimates from the back of the envelope, but there are like several references in the literature of people who achieve these numbers. So it's not a far-fetched thing. It's not that I came up with some new stuff that will, you know, achieve a higher sensitivity. This is really, it exists in several labs around the world. So with these membranes, you can have like displacement sensitivities of 10⁻15 meters per square root of hertz. Okay, of course, it's not 10⁻15 meters absolute. It's not like a DC thing, you know. It's not as if the membrane moves and you can sense it with 10⁻15 meters. But if you integrate for a while, you know, and this thing is moving, you can have a sensitivity of 10⁻15 meters, let's say. So these are some forces which I expect to see in our setup. So the best force sensitivity we expect is around this 10⁻16 newtons, let's say, a bit higher, 10⁻15 newtons, say. This is residual gas pressure. Coulomb, if my membrane and my microsphere are a little bit charged, you can get rid of that by illuminating with UV light. So that's also something we're going to have to do to kick out electrons. I mean, people have characterized this very well. These silica microspheres, if you illuminate them with UV light, you can even look at like single electron. You kick out 1 electron at a time, and you put them among electrodes, and you monitor the motion, and you can really see that you're discharging your sphere electron by electron. Casimir force is also something you should watch out for, but even though at the regime that we are operating here, it's probably negligible. We probably won't be able to see it. And of course, gravity, which would be nice. It's this black one here, but it's completely off any expectation. I mean, I don't expect to see gravity in this experiment. It's just too hard, too weak. And every time I give a talk, someone comes up with a new background which I overlooked. So please, if you have a new background, tell me. But anyway, these are all going to have to be like characterized very well and so on before you are actually able to see something. But that's part of the process of developing the technology. That's what one have to do. So what could we do? We could search for new forces of nature. So one idea is to search for those non-Newtonian forces. Several people have done that in several different systems. So this is an exclusion plot from a famous review article on the low energy frontier of high energy physics, let's say, no, fundamental physics. So you could postulate a new scalar field which couples to electromagnetic interactions in this way with the coupling constant, which you parameterize like this. And due to this Feynman diagram here, so you have like a standard model particle, it emits photons that self-interact with it, and then these photons can exchange the scalar particle, so it's an indirect interaction. And this will lead to a potential Yukawa-type potential, which is roughly proportional to the product of the number of nucleons on each of your samples, inversely proportional to the distance, and it's damped by an exponential factor which goes with the mass of the particle. Okay, so you can place the mass here, and this is the interaction strength. So this is basically, it's a different letter here. It's log m, but it's basically log lambda. So I took it from a paper where they call it m, but here I call it lambda. And you can exclude it, you know, so the motion of the Earth-Moon excluded. I mean, torsion balances excluded. There are other experiments here, more torsion balances, some Casimir force experiments. These things are excluded. We expect to go a bit beyond that, you know, with this sort of micro-membrane and microsphere apparatus, we expect to exclude a little bit more. So this yellow region here is essentially this side of the plot, which I have taken and replotted here in my own way. And the blue region is what I would expect if you approach, say, a 2-micron sphere, about 1 micron to this membrane, with the sensitivities that I quoted before. We would expect to exclude a little bit more in the range of masses and in the coupling of these particles. And what I would like to point out, this always bugs me. I mean, this is not new. This is not something, it's by far, I'm not the first one who points this out, but it bugs me, is that with a simple experiment, it's complicated, but you know, conceptually very simple. It's not, you're not banging high energy particles onto each other in a very complicated way with superconducting magnets or anything. You're just basically approaching two things and looking if they move. You can exclude a physical effect, which you don't know if it exists, of course, but it would be, if it exists, it's relevant only at very high energy scales. So there's this cutoff scale here, which can be very, very high, up to the Planck scale, say, and you can still have a glimpse of what's happening at those high energy scales by looking at like a very indirect effect like this. So this is the general idea, you know, of tabletop fundamental physics experiment. There are not many ideas lying around, but the ones that there are, they are almost all like this. You can exclude very high possibilities, very high energy effects by doing low energy experiments. So somehow you trade sensitivity, you trade like super energies for sensitivity, which is very nice. You can also be agnostic to the form of the force. Normally people parameterize it with this G Newton constant here, referring to gravity, so people want to see if gravity gets modified at small distances. But you could also imagine that there's new forces beyond gravity, which may be stronger than gravity, but they would manifest only at small distances because of this exponential damping here. So generally you exclude this lambda damping, this parameter, against this alpha constant here. And this is a famous plot which people have produced, excluding several models. I mean, don't mind too much. Even I don't understand all these models. You know, this the string theories, they come up with new theories every week, so it's a new model every time you have to exclude. But with Samba, you could maybe push this a little bit further. You know, that's the general idea of the thing. So just to give you an idea of how does the experiment looks like right now, this is my lab. This was in March 2018, though. This is my master's student. I mean, you want to hire him for the PhD, I promise. He's the best guy you will ever have. This is June 2018, so we started to assemble this optical tweezer. This is, yeah, roughly, I've been traveling for almost a month now, you know, conferences and visiting people around the world and so on. This is when I left the lab, more or less at the end of June, how it looked like. This is another angle. This is some quantum optics experiment I was doing there, which is not directly related to what I'm saying here. We're starting to build our first optical tweezer. It sits inside the box, and then inside the box there's another box, and then another box, and these things, you know, if you stand next to it, the sphere goes away, you know? So you have like a glass cover here, and the laser comes up, and you try to levitate these spheres, and you drop them with there's a piece of glass. You make them dirty from these microspheres, and you apply a tension to a piezo. This thing moves, and the spheres fall down, and eventually they fall all the way down to the focal point of the laser, and they get caught there. That's what you hope to. So you have to try a couple of times to get the sphere. I mean, we've managed to see some trapped microspheres, but they last very few, for the moment. And the reason is, I've been talking to some people who have experience with this. I was visiting Marcus Aspelmeyer last week, and I also have another friend in Yale University who's working on similar experiments. And the reason is, apparently, to trap a sphere in atmospheric pressure is harder than trapping it in vacuum. Now, trapping in high vacuum is hard because you have no damping, and then if your sphere has some motion, it just goes away and you lose it very easily. You need an active feedback to keep it. You need to control the power of the laser to keep it always stable. Turns out that in the air, there's a lot of wind motion, which for us is negligible, but for the poor sphere with a 10 to minus 13 kilogram mass, it just blows away, you know, it's like a tsunami, like a hurricane. So the idea, you need to have like a, I don't know, slight vacuum, like 1 millibar, and that's the easiest point. So that's what we're gonna try now. We're at the point of, you know, finishing up this vacuum chamber. You know, it's complicated. You know, you have to build your own vacuum chamber. We don't have much money to buy our own like fancy vacuum chambers or anything. So you have to improvise a lot of stuff. So that's the point we're at now. So these microspheres, I mean, maybe I'll tell you, it's a nice story about it. I wanted to buy them from a Brazilian company, but I don't know of any Brazilian company that produces microspheres, silicon microspheres. So I was looking and looking and looking for a while, and I figured out that these things are used in cosmetics industry. So I phoned up some cosmetics companies, and I said, I heard you have microspheres. Can you sell me some? And the woman was like, yeah, how many kilos do you want? I was like, oh, look, I want, I don't want kilos. I want, okay, we'll send you some samples for free. So they sent us basically spheres forever. You know, we have from 2 micron all the way to 20 micron. We have like a whole bunch of spheres, and it's super. They are careless about the way they make their spheres. So you open this pot and the spheres go jumping all over it. It's terrible. But anyway. Actually, that might also be a bit of the reason why we don't manage to trap them yet for a reasonable time. If the spheres are not, you know, perfectly spherical and nice, it becomes much harder to trap them. So that's. I've heard stories of people in the business that they try to trap microspheres from, I don't know, some random less known companies, and they have a hard time on that. Anyway, we're also building cavities, and I already have this membrane, so we're starting to go for this, you know, putting it all together. The laser hasn't arrived yet, but it should arrive within the next few weeks and so or so. This is just some advertisement. I mean, if you have an Instagram account, you can follow us on Instagram. We have an Instagram page we update every time with lab stuff. And it's really just very stupid things, you know. We get electrified in the lab. Oh, cool, let's take a picture and put it on Instagram. Some informative stuff, you know. It's the beginning, you know. It's mostly my student and the students that take care of this. I'm sorry for those who don't speak Portuguese, but this is a WhatsApp message I got from my student one day. He said, reasons to do science. Discover how the universe works? No. Make people's better with technology? No. Get Instagram's likes? Yes. That's a proper reason. So these are the people involved. There is me. There's Bruno. He's a master's student. He's actually from an engineering background, but you know he has the lifestyle of a physicist. So he's doing a master in physics now. Paulo is a friend of mine who is a theorist. He's starting to get a bit involved in the theory of this. We talk a lot to George Svetlichny. I mean, he's not actually involved in any of the experiment, but he's a major figure. He's there at PUC, so he's a very good friend of mine. And he's a crazy, crazy, crazy physicist. I mean, cool guy to talk, you know? And so he comes up with all sorts of crazy ideas. Why don't you try that? I mean, we're not yet at the point of trying any crazy ideas, but it's good to talk to him anyway. And we got the support of the Serra Pilheira Institute, which is a private institution that aims at funding basic research in Brazil. Something really nice, really big now that it's starting. And we're housed in the Setuc laboratory. Of course, I arrived at PUC and had no lab, so I thought, please, can I use your lab? So these guys are fantastic. They let me go in the lab and use everything, and it's wonderful. So thank you very much.
Okay, questions?